bedrock limestone. So surface water directly enters the aquifer. Here in West Virginia, we have what's called the Greenbrier Limestone Group. It's prevalent throughout the state. Here in the area of interest, the Elk River and Big Spring Fork, it's about 350 feet thick. I know you can't read that, but there's a series of limestone and shales that make up the Greenbrier group. The top group is the Alderson limestone, then an insoluble Greenville shale, then the Union limestone, Pickaway limestone, and then the Taggart shale formation, which is also insoluble, and then Patton limestone and the Sinks Groves limestone. And what happens is this layering of limestone and shale controls cave development, which we'll talk about later. But also you'll notice where the limestone is shown, it shows a block graphic, and basically that's representing cracks in the limestone. The vertical cracks are called joints, and the horizontal cracks are called bedding planes, and that's where the water flows, and that's where the caves form, and we'll talk about that later.
Do we have all of those forms in Slady Fork?
Yeah, essentially, at some point, yes. They're varying thicknesses. If you go down in like Greenbrier County, the whole series is about 600, 700 feet thick, and then as you go farther north in the state, it gets thinner. But around Slady Fork, it's 350, and you do have all these represented. The Union limestone is one we'll see a photo of. It's the most chemically pure, and that's the one they typically want to quarry for limestone operations, for rock things like that. How do caves form? Basically, you have the soluble limestone bedrock. You have the vertical joints, the horizontal bedding planes. You have surface water that falls as rain or snowmelt. It passes through the topsoil layer, which contains organic debris. As it passes through the organic debris, it picks up carbon dioxide, which is a byproduct of the organic decomposition. And by picking up the carbon dioxide, the water becomes acidic. It forms carbonic acid. And that's the key to cave formation, is this acidic water then flows down into the limestone. And as it flows into the path of least resistance is through the vertical cracks or the horizontal bedding planes. And as that acidic water flows through those openings, it's dissolving the walls of the joints and the bedding planes away, and it's enlarging those passages, and that's how caves form. So it's essentially acidic dissolution of the limestone. A little bit about groundwater flow in Karst. As I mentioned, surface streams are non-existent or they're intermittent. We see that with the Big Spring Fork. Groundwater flow in Karst is predominantly through underground conduits in the limestone, through the caves and the underground streams. Surface water is captured by sinkholes or caves as it crosses the limestone and directly enters the underground aquifer. And then these streams rise to the surface as springs or stream resurgences where they meet insoluble rock. So if they hit a shale, they'll rise up to the surface as a spring. And these springs and cave streams are often sustain the water flow, the cool temperatures, and the aquatic habitats of our headwater streams. This hollow nature of Karst results in a very high pollution potential because you have the direct flow of the groundwater or the rain and surface water into the groundwater, essentially bypassing any natural filtration that topsoil may provide. Groundwater contamination travels quite rapidly through these underground networks, up to thousands of feet or even miles per day. So any contaminants are transmitted very rapidly, and these can contaminate wells and springs in the Karst area. And just as a reference, if you put a contaminant in normal soil, it typically travels at rates of feet per year. So if you spill a quart of oil in your driveway, it's not going to contaminate a huge area. It's going to take a long time to spread out as it flows through the soil. But if you spill that quart of oil in a Karst area and it gets down into the cave stream, it's basically going to flow the same speed as the cave stream, which is measured in feet per second. So a lot faster transportation rate. And again, often in rural Karst areas, most folks get their drinking water from private or municipal wells. So any contamination of the Karst is going to contaminate those drinking water sources. Unless Karst watersheds are properly managed, the direct connection between the surface and subsurface streams can threaten local water quality. The safest watersheds are those in which all residents understand the relationship of groundwater flow in the landscape and work together to reduce soil erosion, high-density development, agricultural and urban stormwater runoff, overgrazing, improper waste disposal, and pollution. Okay, this is This map is a Karst map of the Upper Elk. The green line represents the watershed boundary, so any rain that falls within the barriers of the green line basically is considered part of the Upper Elk watershed. Anything outside, like here to the north is the Tigard, this would be Clover Lick and the Greenbrier, and over here would be the Gauley. All this is the Upper Elk. The yellow areas represent areas where limestone is exposed or shallow, so these are the karst areas. And if you look, this is Dry Branch, Big Spring Fork. So here is Beckwith Lumber would be right here, Route 219 going northward. The ski barn would be in this area, and the ski resorts would be up in here on the mountain. And so basically the limestone is exposed the entire length of the valley. This is Old Field Fork coming north from Marlton, essentially follows Route 219. A little bit up Slady Fork Creek, there's a little bit of limestone exposed up Slady Fork. And then this is the Elk River. Here where Old Field Fork and Big Spring Fork meet is where the Elk River starts. And then down here, just below Beckwith Lumber, there's a section where there is no karst exposed. The karst is basically buried underneath limestone, and so the elk flows on the surface here year-round. And then about 4 miles south is where we pick up the karst again, right here. And this is where the Elk River goes underground for about 7 more miles before it rises at the Cougar Mill Spring. And so in the summertime, we'll see photos of this. The Elk River is essentially dry and flowing in its underground passage. Little history. This is from a book by Hugh Maxwell. It's written in 1898. It's the history of Randolph County. It talks about the black hole. It says, theory and all known facts lead to the conclusion that a cave of enormous dimensions exists in Randolph County under or near the course of the Elk River between the Pocahontas County line and the mouth of Valley Fork 6 miles below. But no one has yet ever found an entrance into the cave, and its existence cannot be positively affirmed. Facts which are explained on the theory of a vast cave are these. Elk River, except in times of freshet, flows into a crevice at the foot of the mountain, or when very low, disappears among the boulders of its channel. And 6 miles below, the water rushes to the surface. Its underground course is through limestone, and it must flow through galleries of large size. In 1896, near the point where the water sinks, a portion of the river bottom dropped down, leaving an opening 15-foot square into which the whole river plunged and disappeared. No bottom was visible, and no one attempted to enter or examine. The next flood filled the opening with boulders. So this is an example of the sinkhole collapse that happened in 1896, and how temporary it is, how sudden it is, and how temporary it is. But this is documented in the local history book. But it also talks about the Elk River. Now, we're going to see photos. It talks about how no one had found the cave of the underground elk, and we're going to see photos. It was basically discovered in the early 80s. And we have some photos in here that show the underground Elk River. This is the location that's described in the book. This is the black hole. This is where the Elk River goes underground. This is looking upstream. These pictures were taken in October. And so you've got the Elk River flowing in its bed. This is an upstream view and a downstream view. And so it's flowing past, and you can see the rocks are becoming exposed. It's basically starting to sink in its bed because it's crossing onto the exposed limestone now. But over here to the left, about at this point in the photo, is this little surface stream where the river is actually being powered down into the cave. And I've got a little video here that we can watch for a few seconds. Let me advance it. There's looking downstream. And you can see the leaves. The leaves are flowing. This is about 6 foot wide here. And there's a view upstream, the water coming from up toward Beckwith Lumber. So you can see not all of it's going into the black hole. Some of it's going down. About 200 yards down to the streams, the river was dry. We walked across dry boulders to get across it. and this is where it goes underground. Now, 20 years ago, I was here, took a picture of this entrance, and it was actually an arched leg, so this has collapsed in the last 20 years. These rocks have collapsed down and closed, essentially closed the black hole entrance. Still water can flow in, but it was much larger before. So this goes into the underground elk, and this is a picture. This waterfall here is, the black hole is about 100 yards away. So the water we saw going underground flows through a small passage and then into this large room, and it drops as this 35 to 40 foot waterfall. And it's called the Taggart Falls. It's in my cave. That's the name of the cave. It takes a couple hours to get back to this point. But there's a large pool here to the right, and that's the last point of the underground elk river that was known until the early 1980s. This is the top of the waterfall, and this person came in through that entrance that has collapsed that we just saw. She evidently came in through the black hole through a crawl, so this is the top of the waterfall. And this is the underground elk river. This cave was discovered, like I said, in the early 80s. The only way to get into it is through a stream bed. It has to be very dry conditions. It's a very dangerous cave. If it would happen to rain while you're in there, the cave would fill up with water, and so obviously you don't want to be in this cave in that situation. But they discovered it in the mid-80s, or early 80s. There's the underground elk river on the left. Some climb-down passages in the same cave. You can see the rock is kind of fluted and sharp, and that's just erosional. That's the water eroding the rock is what causes those flukes. Got a picture of a large room in the cave. This picture here looks like a reflection, but this is actually all dry rock. So here's a bed of, this is probably shale with limestone above it and below it, and then the cave we're straddling a canyon. This is what the bed of the Elk River looks like after the elk goes underground. And this is the Union limestone that I was talking about earlier. This is very pure. You can see it's very clean looking, very gray. You can see how pretty its solution is because it's chemically pure. The water's dissolved it and made these really pretty formations in the rock. But this is what the Elk River looks like in the summertime below Black Hole until you get down to the spring at Cooper Mill. Essentially dry unless we have a very strong thunderstorm that fills up the passage. Okay, so up at Slady Fork, this is a map. Slady Fork area. Beckwith Lumber would be right here where the arrow is. This is the proposed site right here in the bend in the river, and we'll show some more detail there later. 219 is the green line. This is the intersection at Linwood. This is the CC Road. Going across the Cass, your Snowshoe Drive, and 219 going north to Mace. So if you look, every one of those numbers and symbols is either a cave or a spring. Basically, the resorts are here. The pipeline will come down and follow Big Spring Fork. And so as you see to the site here, we're crossing almost all the major springs and caves in the area are along the proposed corridor of the pipeline. In this valley, as small as it is, there are 68 caves or springs. They're listed here and on this page. This is a picture of the Big Spring Fork. The photo on the left is during the spring, after spring rain and snow melt. You have the cave passages are filled and you have water flowing in the surface bed. The picture on the right would be during the summer or the fall or possibly the winter when there's not a lot of flow, and all the flow is the cave passages underneath are able to capture and handle all the surface flow, and so basically there's no flow in the surface bed. And you can see this photo is taken at the same location by the tree there. This is a picture where the Big Spring Fork sinks the last time before you get to the site. This is just across the road from the Sharp store. You can see the barn here. Basically, the covered bridge would be at your back here. And there's a little video here that shows it sinking. Replay that. You can see the water is flowing down into the rocks like a little bathtub drain. And so this is where the water is going into the underground passages. Okay, back to the map. Just a little bit about the hydrology. Sharps Cave is the most significant cave in the area. It has about 4 miles of passage. Essentially, the Big Spring Fork resurges as a large spring and split rock pool just upstream of the meadow where Sharps Cave is located. And then just downstream, about a quarter mile, it sinks. There's a major sink in the stream bed, and that water then flows into Sharps Cave. There's a stream that runs in the lower passages of Sharps Cave. That is essentially the Big Spring Fork, and it flows down to the big resurgence at the Big Spring Fork Spring Complex, which we'll show photos of later. There's another large swallow hole in the valley across from Sharps Cave. It's called Cemetery Swallow Hole. And all these, both were dye-traced. The sink below Split Rock Pool was dye-traced to Sharps Cave. And then the water from Sharps Cave at the westernmost point in the cave was dye-traced to Big Spring Fork. And then Cemetery Swallow Hole was also dye-traced. So this large spring down here by the site is basically the underground water rising back to the surface for the final time before you go onto the sandstone. Just a quick view of Sharps Cave. There's a map here. I know you can't read this. There's 2 levels. There's an upper level, which is dry, very large passages. This is the older part of the cave. It's no longer actively forming because it's basically eroded down into the lower level, which is where the active stream is. So this is the Big Spring Fork flowing underground here in this lower passage. It gets down here to a point where it sumps, where basically there's a pool, and we can't go any further unless we dive. That's called a sump. And then that's where the water has been traced downstream to the Big Spring Fork Spring Complex. But there is an active stream here, and it is the Big Spring Fork flowing underground. Just for reference, the red is the upper section of Sharps Cave, and then there's like a black line that's kind of like a snake underneath. That's the lower section of Sharps Cave. This is Route 219 through here, the roadside park. This spring is Split Rock Pool. So basically you have the spring rising, flows down to right here, starts to go underground. That's where it enters Sharps Cave, flows through the lower passage. And the pipeline here, just below Split Rock Pool, crosses back across the road and then follows on the north side. And we have a concern here of the pipeline crossing. This part of the cave is known as the Root Canal. It's a mazy section. It's within about 17 feet of the surface, and so it's very close to the surface. And we have a concern about the proximity of this to a pumping station in the project. And we'll talk about that later as well. Just a quick photo tour. These are all taken in Sharps Cave. You get an idea of the size of the rooms. As you look at these, you can see the cavers in the pictures to give you a kind of an idea of the scale. This is one of the underground streams. I don't think this is the main stream. I think this is a side stream. There's a caver sitting here, and one here, and one there. This is the waterfall in Sharps Cave. This is one of the high points of most of the recreation cavers trips is to go see this waterfall. This is the underground Big Spring Fork. This is taken under low flow conditions. I understand that when it's high, it sounds like Niagara Falls, and you probably don't want to be in there. There's actually 2 streams. There's another stream that comes out of a crack in the wall here behind the caver that comes from a different source, but this is all water from the Big Spring Fork that flows through the cave. Now we're down in the lower stream passage. It's hard to see, but he's standing in water. And this is back in the upper section that's dry. Again, the large passages. This is no longer actively forming because there's no stream that's eroding the rock. So this is all the bigger it's going to get, but the lower section is still forming.
George?
Yeah.
Can the lower section, by it still being forming, make the upper section collapse?
Oh, sure. most significant cave in the valley is Billy Clay Pit. It's a vertical cave, and so you can see because of the limestone is 350 feet thick, you can have some pretty extensive vertical elevations underground here in the valley. And Billy Clay Pit is an example of a vertical cave. You have to rappel to get into this cave and climb back out, climb back up the rope. So it's not typically a cave that's visited by everyone. You have to have some skills. And because of that, there's very pretty formations in here because they haven't been vandalized. So you have very pristine cave formations in this one. Split rock pool is a surface feature. I think most folks have probably seen it. This is the Morning Glory Inn, and this is the entrance to Slady Ridge. And this is one of the large resurgences of Big Spring Fork as it makes its way down the valley. This photo was taken in April, so there's been some rain and some snow melt. So you have a little bit of surface flow, but in the summertime, all this above is dry, and you have water that comes rising out of the split here, and that's why it's called Split Rock Pool. But in the summertime, there's a big pool below here. I don't think I have an image of the pool. No. This is one of the other large springs that's on the Big Spring Fork. So now let's get specific to the project, talk about some issues and concerns. Start first with the pipeline routing, and then we'll talk a little bit about the site. Back to the map. This is just the schematic representation. We have the ski resorts up in this area. Breed the pipeline off the mountain. Essentially follow the stream down to the site. So what we have is about 5 miles of 10-inch PVC pipeline that crosses the Karst. In it, there's hundreds of manholes and thousands of piping joints. Through this pipeline, there will be 1.5 million gallons per day of raw sewage transported across the Karst. And with sewer lines ultimately leak. There's something called infiltration, which is a concern to engineers who design these plants, that because the pipelines leak, when the groundwater is above the sewer line, you actually get groundwater flowing into the pipe and into the treatment plant, so they have to make accommodations for that additional water in their design of the treatment plant. So they're allowed 200 gallons per day per inch of pipe diameter per mile of pipeline to add to the plant capacity. Well, if that leak occurs and the groundwater is below, the water table is below the pipeline, that leakage is going to be out. So anytime you have a failed gasket or a failed joint or a crack in the pipe or a crack in a seal between a manhole and where the pipe makes its penetration into the manhole, those leaks will be out if the water table is below the pipeline. And typically in Karst, as we've seen, the water table is below because you're flowing in the cave passages. All the water is flowing in the cave passages versus saturating the ground and flowing through the ground.
George, what would happen? These leaks you're speaking of, oil rupture of the line, if it went into one of those caves, and of course we have people downstream who are using this water, how long would it take for to clean that up, or is there any way to clean it up?
Well, and Roger can help me here. Our only example that we know of is at Mammoth Cave. There was a lagoon that failed. The wall, or the dike of the lagoon failed and went directly into the cave there in Kentucky near Mammoth Cave, and they said it took 20 years for them to see the water actually return to the quality that it was prior to the event. Now you asked what would happen. This is raw sewage that we're talking about here. This isn't, a plant that's being misoperated and it's poor quality effluent. It's not water from a septic tank. This is actually raw sewage. You're going to have solids and plastics and everything else. So that's what we're talking about could leak in to the caves of the ground or the groundwater system. That's the concern, is that it is raw sewage. Okay, I've talked. Any leakage will be out of the pipeline because the water table will be below the pipeline, and of course the concern is contamination of the groundwater in public wells with raw sewage. This is not a risk today because there's no raw sewage in the valley today, and I mentioned the Kentucky Mammoth Cave. But basically one leak could impact the water quality or water supply and development for many years in the Slady Fork area. Next issue, I mentioned this, the pumping station that's located over near the shallow passages of Sharp's Cave. The root canal passage, the reason it's named the root canal is there's actually tree or plant roots that protrude from the cave ceiling. So it's a very shallow passage that's within about 17 or 18 feet of the surface. The pumping station wet well depth is 25 feet below grade, so obviously there's a potential to intercept 7 to 8 feet of cave. And there's also a risk that the cave itself, through collapse, could destabilize this large pumping station foundation or sunk. And then, of course, any failure of that pumping station, if the pump shuts down, if there's a physical failure of the foundation or the piping, you're going to have the same issue with the pipeline. You're going to have raw sewage leaking, and it's going to directly enter Shark's Cave through that root canal passage and contaminate the cave stream, and then anything downstream.
Is it true or reasonable to think that small leaks could go undetected for a long period of time?
I think large leaks could probably go undetected for a while, because you really, the only way you could detect a leak out would be to monitor flows. Or I really don't know how you would, unless you did a periodic physical inspection, I don't think you could detect it. Obviously if the flow stopped, if it was a catastrophic failure and the pipeline collapsed or something, they stopped getting flow down the plant, that would be obvious. But I really don't know of any way that you could detect a small leak or even something less than catastrophic.
George, this particular spot right here basically has two problems working against it. Besides the ground erosion, the plants are actually spreading things apart too, aren't they?
Say again, the plant? No.
The roots are moving?
No, they will fall in cracks in the soil or in the rock. They really don't put any stress on the rock.
Okay.
And then last with the pipeline, the effluent line passes directly upstream of the Big Spring Fork Spring Complex, which we'll see photos of here, and downstream of several other springs that are in the area. The effluent line is gravity flow. It's going to be buried at a depth of about 5 feet. The soil depth in this area is about 5 feet, so we're anticipating there's going to be some excavation of limestone. So very high potential to intercept the shallow underground stream passage. And the reason I say it's shallow is because it rises to the surface here in this big pool just downstream. It's very close to the surface in this area, the underground stream is. So the risk is a negative impact on the spring. Could cause a collapse or a flow interruption or restriction of the flow, which is obviously going to back water up. It's going to come out somewhere else. We don't know where. It could be on the site. It could be upstream anywhere if that spring gets collapsed. This is the cold water spring that supports the downstream fisheries. And so you would have, if something impacts this spring, it's going to impact the reproducing rainbow, brown, and brook trout that are downstream in the Big Spring Fork and the Upper Elk. And then the other issue is there's a plan to run the effluent line directly through the spring pool. I don't know if that's still the case or not, but obviously that has potential to impact the spring itself, or the action of the water rising from the spring to actually cause physical stresses on the effluent pipeline. And we'll see some examples of the flow, some of the velocity and the force of the flow coming out of the spring during high flow here. A site. Again, the site is here. My cursor. This is a bend in the Big Spring Fork. This is the meadow. And you can see all the karst features here that are local to the site. The aerial photo. Again, here's the bend in the river. The yellow encompasses the proposed site. Each one of these is either a spring. This is the large spring. We'll see photos of that. We have photos and videos of each of these. But there's a stream that comes off of Middle Mountain and flows across the site. There is no channel from about halfway across the site to the Big Spring Fork. It basically sinks in the middle of the site. And if you go there when it's raining, there's water coming off the mountain, and then it disappears right in this area. And then there's a flow coming out down here on the western edge of the meadow. And so this flow coming off the mountain is more than likely flowing in an enlarged joint here underneath the site. And this is the area where the voids were found as well. And I'll just show, this is V1 is this spring over here on the mountainside. And then V2 is here. V3, V4 is the large one. V5 and V6 is just a shot of the river. So this is water coming out of, this is one of the springs coming out of the side of the mountain. This is after a rain, so you can see there's pretty significant flow. And it doesn't normally flow, so it's knocking the grass down, finding a path across the meadow. I'll show this one. This is the Big Spring Fork Spring Complex. So you can see the force of the water actually boiling up here. And this stream is completely coming out of the ground. This is all spring from water from the spring itself. This is not the Big Spring Fork. This flows stream down about 100 yards downstream and joins the Big Spring Fork. So all this water that we're seeing is coming out of this one spring pool. And this is the spring pool where the effluent line was going to cross through. As you see, quite a bit of flow. And then this is the little rise that comes off the edge of the site. This is the water from Middle Mountain. Try that again. So this is the water that's coming off Middle Mountain and rising on the edge of the western edge of the site. This is the Big Spring Fork Spring. In winter, spring, summer, and fall. So you can see different times of the year, different water levels. And this is about 30 to 40 foot diameter spring pool. It is one of the larger spring pools that I've seen in West Virginia. Let's see, we just saw that video. This is a picture from October. And so you can see this still water coming out. This is still the springs. You can see a little leaf floating there, give you an idea of how much water is coming out of it in October. So just to show the variation in the flow. But this is the rise, the final rising point of all the water that goes underground, coming out of Sharp's Cave and that cemetery swallow hole. So that dye tracing study, this is where the dye was traced to. Back to the site. This big bend in the river was basically formed from alluvial soil that was deposited. It's been washed down by this stream over thousands of years, basically deposited here with time, and so it's created, actually pushed the river, the stream out around the field in this bend. And so what that means is we can look at the stream bed, the bedrock that's exposed in the stream bed is essentially the same as what's under the proposed site. So by looking at the bedrock in the stream bed, we can infer what's underneath the soil on the site. So if you look, this is what the stream bed looks like. Upstream of the site, you can see the exposed limestone, you can see the cracks, the vertical joints. We won't see the horizontal bedding planes because they're obviously underneath, but this is a good example of jointed limestone. And you can see it may not be that thick. This is about 6 inches thick. Again, this is upstream of the site. But as you walk down, you see that it looks like it's solid limestone, but it's about 6 inches thick. And as you get downstream, everything's buried in cobbles. Walk toward the site. You get down past the site, you start to see the limestone again coming out of the cobbles. And you can see it's very uneven surface, very fractured. You can see the joints here are so large they're actually filled with stream cobbles. So this is like 6-inch stream cobbles here. This is probably about a foot wide. Very uneven surface. This is directly west of the site, so this is after the bend. The 219 bridge is just starting to be visible here. So the site is over here to the right. Again, just examples of large joints. Okay, concerns on the site, there were voids detected from the microgravity and the core drilling studies. Some of these were over 1.5 feet in height and were also stacked. And when we say voids, we're talking they drilled down, went through the soil, went through solid rock, and then hit a gap for 1.5 feet or more, and then hit rock again. And so basically it's representing a void, which is going to be a cave passage or an underground stream channel. And the risk here is, if you build on top of something with a void, it could collapse. And the SBRs together weigh over 5 million pounds. And so there's incomplete assessments underneath the critical equipment, both core drilling and microgravity studies. High risk is sinkhole or void collapse. high risk of surface and karst flooding on the site, risk for damage to the facilities, foundations, resulting in loss of containment of the raw sewage to the surface stream or to the underground streams. Basically, if one of these voids would collapse underneath the foundation, causing the equipment or piping to fail, you're going to have a spill and contaminate the groundwater of the surface stream. So the financial risks are high. High construction costs, potential for emergency repair if a failure occurs, and then also high potential for business interruption if a failure occurs. And if the plant gets shut down because it's physically failed, then what happens upstream? All the businesses and the residences that depend on this plant are going to have to shut down, or the flow is going to have to be diverted to the river, which I don't think anyone wants.
How about that cause some trouble with
This is some pictures of some recent sinkhole development in the area. This is a meadow where the effluent line will be routed. These are some of the pictures of the springs that we showed earlier. These are showing them in dry season, but these have basically all formed within the last 10 years. So it's a very dynamic situation. You can see the dirt's fresh. Here's a couple more. Here's the highway going here, and Miss Shelton's trailer is here. This is actually the site. The hay bales are on the site. And if you look, this is the water coming out of this same sinkhole after a rain. So this is the issue of karst flooding. Even though you build a flood wall to divert the stream, at high level around it, you can still have karst flooding. You still have underground water coming up through the soil and causing flooding and damage to your site as well. And this one's sideways, I apologize, but this is actually showing water that's coming from the edge of the highway and flowing northward, opposite of the direction you would think, and flowing northward. So again, just demonstrating how dynamic this whole area is. Back to sinkhole collapse. This is a recent sinkhole that opened up beside the bed and breakfast at Sharps. This started out as about a 3-foot diameter hole, and when you walk up to it, it was actually about 15 feet deep and delved out. So we were standing on cantilever dirt to go up and look into this thing, and they dropped a camera in. This was in November 2005 when this first opened. You can see the fog coming out is from a cave. That's the cool air from a cave. The cool, moist air from the cave. Actually, it's warm, moist air since it's November, and it's hitting the cold air in November and causing it to fog. So that's what you're seeing there. But there is a cave in there somewhere. Let's jump backwards. Let's see if I can force it. Okay, so that was in November 2005. This was February 2007 after a large rain. Basically all that soil collapsed. And you can see water flowing. This is the top of the limestone, so there's water flowing across the top and then falling down into this cave. And for scale, this rock is probably 5 or 6 feet across. It's too big to pick up. And then, this is just in the last month or so. It's collapsed even. Actually, it plugged up completely with soil. We were going to dig it open, and it came, it was full of dirt. And then 3 days later, we came back, and it had collapsed again. And each time it's getting bigger. And this, again, this rock's about 5 foot, the stick's about 6 foot long. Thinking about getting a strap trying to pull this out with a pickup truck, that's how big it is. But there's obviously a cave here and water flowing into the cave. So again, this has all happened in the last 18 months. This is a huge sinkhole. The diameter is probably 20 foot around where the edges of the sod are. It's probably 20 foot in diameter. And down at the bottom, it's probably probably 8 to 10 feet in diameter, and then, like I said, that rock's about 6 foot. The crack is pretty small underneath.
That's just across the road
It's right beside just north of the bed and breakfast, within 30 feet of the house.
so it's just across the road from the site.
It's upstream about a quarter mile. Right there where the red bridge is, it's in the meadow across from the covered bridge. What we're trying to show here is, the sinkholes in the area. There was no indication that this was here prior to November of 2005. It was just a grassy field, and then all of a sudden this hole collapsed, and now it's gotten huge. And this is just an example of the dynamics of the karst. Sinkhole. Any farmer that has limestone knows about sinkhole collapse. It happens unexpectedly. This is a pretty dramatic example of sinkhole collapse. This is in Bowling Green, Kentucky. Obviously, it's huge, 200 foot in diameter, 25 foot deep. This is a good aerial photo of it. But I wanted to draw attention to this photo here. This is a sewer line that broke in this collapse, and so this is the risk. It didn't break the line; it actually pulled it apart at the joint. So it basically just pulled the joint apart. Obviously, the sewage is going down into the cave, and that's the risk that we're concerned about here. Because anywhere along the pipeline, even though the pipe may be well built and maintained, if it's built over a void, like we just saw a sinkhole, and that sinkhole collapses, it's just going to pull the pipe with it, and then you're going to end up with sewage going into the underground stream. Flooding concerns. This is upstream of the site. This is obviously in dry conditions, and then during a flooding event. You see, it's almost crossing the road. So, just to wrap up, the project as currently planned is not safe. There's a high risk of sinkhole collapse, resulting in structural damage, equipment damage, or piping damage. There's site flooding issues. The concern is if there is a loss of containment, that there's downstream or underground contamination of the groundwater or the surface water. Obviously concerned about unidentified problems along the pipeline or the site, and these include the voids. The project will continue to be expensive. As Roger said, you can build the plant as long as you have money, but construction costs on Karst are typically high. The future risks, if there's any failure, there's going to be expensive repairs. Who's going to pay for that? There's going to have to be emergency funding to fix the plant. There'll be business interruptions, cleanup costs, long-term damage to the groundwater.
Can't clean it up.
That's right. What are the contributing factors? Lack of knowledge of the local karst and hydrology, incomplete assessments or risk analysis, lack of consideration for public and expert input, no clear project ownership or objectives, and no environmental impact statement prepared. What's the solution? We need to stop and rethink the project now. We need to consider what we do know and what we may not know, and consider the risks and potential consequences of both. As difficult as this may be, it will be less expensive than continuing on the current and uncertain path. This requires bold leadership. What do we recommend? We recommend that a rural wastewater planning workshop is conducted. We can look at other communities with similar issues for examples. Basically have this session facilitated by a group that's experienced with rural wastewater planning. Have all stakeholders involved, includes the community, public service district, business interests, landowners, second home, the property owners, recreation groups, conservation groups, developers, and the engineering firm. Clearly identify and communicate the needs and goals of all stakeholders. Develop a community ownership of the objectives and the solution. And we consider current and future situation, the problems with the existing treatment facilities, whether it's technology-related, operational issues, or capacity issues. Look at monitoring the stream, doing full stream monitoring to quantify where and what the existing situation is. Look at geographical locations, and that is looking at today, where do we have issues, and then where do we have needs in the future with development? Where are we going to plan to develop? Prioritize the issues, develop a solution plan, prepare a comprehensive environmental impact statement, and develop the scope, cost, and schedule for each solution if there are multiple solutions. The outcome, we have clear project goals and a plan for moving forward. We have stakeholders issues addressed or at least acknowledged. We have a cost-effective solution using the best technology. All environmental issues are addressed. We have a balanced solution between recreation, environment, and development. And we end up with a long-term, low-risk solution, which is also a safe and sustainable solution. We have a sense of ownership by all stakeholders. We have transparency and confidence in the work process. And we have community building versus community dividing, which is where we are today. It's a win-win situation for all. Possible alternatives, membrane retrofits of the large plants and clustered systems for future development in the valley. Our action that we request, we request the members of the Pocahontas Public Service District to make a motion and vote to take the following immediate action. Put the project on hold and conduct a facilitated wastewater planning workshop with all stakeholders to define clear project issues, goals, objectives, develop a safe and sustainable project that will serve the community needs while protecting the unique natural resources of the Upper Elk watershed. This action is supported, or this recommendation is supported by the Elk Headwaters Watershed Association, the National Speleological Society, the Snowshoe Property Owners Council, the West Virginia chapter of the Isaac Walton League, the West Virginia chapter of the Sierra Club, the West Virginia Highlands Conservancy, and the West Virginia Outdoor Sportsmen Association, as well as other folks who have voiced their support tonight. Okay, that's the end. I can take questions. We could do Roger's demonstration and take questions later. So, or we can take a break. I know it's been a while. It's been an hour. I'm sure you all need a break. We're going to do questions first and then take a break? Okay. Let's take 5 minutes, let Roger set up, and then we can...
Dr. Science is here from out of town, and this is the lively part of the show, and I came to demonstrate several things. First thing I want to say is that 8 Rivers Safe Development picked a name that really indicates what it is we want. We are not against development, but we're for safe development. Safe means not only health and the environment, but it also means the conservation of taxpayer funds. Because sooner or later, this plant is going to be built at taxpayer expense, or whatever alternative is probably going to have some component of taxpayer expense. So we think the safety of invested money, invested public money, is also part of what it is we are after. I want to talk about some practical things. We know that the proposed plant is to be built on limestone. Limestone sounds like a very solid rock. In fact, we saw that column, the Union limestone, is a very pure limestone. I have some pieces of Union limestone here. If anybody can tell this by taste, this is Union limestone. I went to great expense and picked it up across the street. We think of limestone as solid rock, and indeed, I could demonstrate that with this plate. This plate is a solid plate. You all know what a solid plate is like. And what I want to demonstrate is that this plate has a lot of strength in compression. Let me demonstrate that. I'll put that plate on the floor. I brought this plank. I'm going to load this plate. This will be good if it works. Try to show you. Whoops. Fortunately, there's another plate. Oh, we dropped a piece out of it. Well, obviously that's pretty good limestone. But what happens in compression is very strong. But that, you see, what we end up is with the limestone that actually exists in the beds of the river, underneath the soil, and wherever limestone is exposed. The cracks, when we try to put Humpty Dumpty back together again, are the joints, the fissures, the cracks, the bedding plane partings. And you can see that it's very difficult to build anything on that. So one of the requirements for building anything it's going to cost a lot of money is to do drilling. You know what's under it. So what happens when you drill through some soil and you hit some of this solid bedrock? Well, most of the time, people stop drilling. They say, oh, we hit bedrock. It's safe to build on this. We can see it's not safe to build on this. And in fact, 40% of the drill holes found a cave. 40%. You say, gee, that's something. Well, they only drilled 7 or 8 holes. So the percentage really looks terrible. But you have to realize there wasn't much investigation of this phenomenon. Now, if I were going to build a house, this might support a house if we have soil over this. But if I'm going to build some large reactor tanks whose combined weight is several million pounds on this, I think we've got a real problem. So that's the first thing I want us to understand. The second thing I want us to understand is this is an ordinary funnel. You all got a funnel in your kitchen, or somebody has. When you look in engineering textbooks and you find one that has a section in it on karst and cave geology, you invariably see a cross-section that looks like this funnel. And what it says is that sinkholes resemble funnels in cross-section. And that sounds pretty easy. And if you're going to build a road across sinkholes, what do? Well, you got to plug the thing, right? So I'm going to show you how easy it is to plug a funnel. Can you help me? Sure. My assistant, George, will help with this. I'm going to ask him to pour some runoff water into the funnel.
You want values or you just want to show?
Oh, that's fine, right there. Okay, let's show everybody. And you can see that my finger is a wonderful plug. That looks great. In a textbook sort of way, right? All right, what happens now? We've effectively plugged this. Let's keep adding water here. Here comes a big deluge of rain. Keep going, keep going. You can see that it's overflowing now, and it goes over to the next sinkhole and disappears. So the idea that a sinkhole can be plugged is a sort of not a very practical idea. In fact, it doesn't work too well. You say, well, don't they recommend that? Oh yes, they recommend that in engineering textbooks. They say, but you don't plug this with just anything. You want to use good limestone rocks. Put in a little tissue paper here to look like the soil that we put into that. All right, now let's see how well this works. We've now plugged the sinkhole effectively. And you see, we've effectively plugged the sinkhole. We can now build our road right over it. Well, that doesn't work so well. We've got to get a better plug, right? Well, what's wrong with this picture? If it's that simple, why can't we fix it? One of the last slides you saw showed a terrible collapse of a sinkhole in Bowling Green, Kentucky. It cost $1 million to fix that road where it fell in. And you say, where are the engineers? Well, they paid for some consulting engineering. Consulting engineering said, you want to move the road so you don't go over an especially large room in the cave here. So they said, thank you very much. Here's your multi-$1,000 for your wonderful consulting. Take that under advisement. Came to build the road. The contractor says, we're going to put the road right here. Well, we think you ought to bend it. Well, hell no, that would cost more money. We're going to put it here so we can put businesses on both sides. So they put the road right across the cave. It began to sag. I heard about it in the newspaper. Reported that some citizens had come down and complained that the road was dipping. And so they consulted the consultant who said, don't build there. And he said, oh, well, it's not a cave. I had called it a cave collapsing. He said it's just that the contractor failed to properly compact the roadbed. About a month later, the whole thing collapsed, dropping 2 trucks and a couple of cars into the hole. $1 million later, egg on their face, egg on everybody's face. So they fixed it, right? Once again, they ignored the consultant's recommendation and essentially put in a 32-inch tile, the bottom of a 30-foot wide, 20-foot high cave passage that floods to the ceiling. Here's this little tube going through and dumped all the fill back in on it. Guess what that road is doing? I went over it the other day and it's starting to dip. We asked them about it and they said, oh, we're monitoring that. Well, I think the next failure is going to be more than $1 million. But we talked about engineering handbooks. Most engineers do not have experience in Karst. They believe the engineering handbook. They might actually believe you can plug sinkholes, but you can't. Let's look at why. A sinkhole doesn't really look like a funnel. It looks like this. Do you know what this is? Motorcycle helmet? What is this? It's a colander, it's called. So now we're going to demonstrate what the problem is on a sinkhole. You can see we can plug the bottom holes. It goes everywhere. Sinkholes drain in every direction. There isn't any effective way to plug a sinkhole. Ask any farmer with sinkholes on the property whether that isn't true or not. Now, we've got one more thing to demonstrate. We have heard that it's very difficult to clean up a Karst spill. In fact, I've heard it argued that pump and treat methods, which are the traditional methods of treating sewage spillage, is big toxic spills and so on. They drill holes and they pump water out for several years, perhaps. We have one located near Dayton that's been pumped and treated for at least 7 years. We're still doing it. It's still got a toxic plume moving. What's the problem in Karst? Well, the thing has gone down into the next county by the time you get the truck there. Let's illustrate another problem. This is a sponge. I'm going to put some of this food color. I assure you this is food color, so we're not. And I'm putting the food color on top of the sponge. And we'll put it there, and what I want to illustrate is that all we have to do is to wash water through this sponge. And every time you put a fresh batch through, we remobilize the food color. Or why don't we squeeze it out here? Well, you can't squeeze out raw sewage in a Karst, but we can do it on a sponge. There, now I've got mostly squeezed out. So you can see I'm still getting contamination. And every time it rains, more contamination goes through. If somebody's downstream monitoring, and it were my sewage plant, I'd say, well, wait till it dries out and we'll come down and sample. Guess what? It's gone down to the next county. But comes the next rain, and we get more contamination. the remobilization of toxic materials, of poisons, of herbicides, of whatever is going into the ground is a serious problem. Down in Kentucky, we've got some heavy metal contamination, and people thought it was cleaned up for 5 years, and then came the big flood, remobilized the sediments, wiped out the starting to recover animals in the cave. All right, that concludes my demonstration, but what I want to end with is this. What we have done is to challenge the finding of no significant impact. Now, I've impacted this floor and everything else. I did bring a mop and a broom. But I've tried to demonstrate that our contention is that the mitigation called for in what we regard as an inadequate investigation, where no environmental impact statement was done, is totally inadequate, is inefficient, and impractical for preventing the kinds of catastrophes that I've kind of reenacted here for you and that George has been talking about. So, we'll take any questions.
Okay, open the floor for questions from anyone.
Supposing I had a well, an artesian well, below that drain, and I was getting good water from it, would I be getting contaminated water from the sewer if it came through there?
If it came from the upstream, from the cave stream, yeah.
And so then I could sue the party that...
That I don't know. Yeah, if the water came from the Karst aquifer and the aquifer was contaminated, then the water would be contaminated.
Okay.
George, what is some of the longest distance that you know of or proven that water runs underground?
You want to take that?
Yeah.
You know more about than I do.
There's a, one of the classic dye traces is about 25 miles in Missouri, where they couldn't understand why the water in their spring was tasting funny. And a fellow I know who's a geohydrologist investigated, and he found that that was coming from 25 miles away. And the problem is, in a normal stream, you have sunlight, and the sunlight and ozone and the aeration work together to partially purify water. Underground, there's no sunlight. So there's virtually no purification. Whatever goes in upstream is what comes out downstream.
I guess locally, the photo that I showed of the waterfall, and I said there was a pool there. And that pool goes underground, the underground Elk River down to Cougar Mill, and that's about 7 miles. Coming into the plane of that picture was another stream that comes from Simmons Mingo Cave. If you all read, I guess about a week, 2 weeks ago, there was a rescue up there. That cave is in Randolph County, up from Mingo, the town of Mingo. And the rain that falls in that valley goes into Simmons Mingo Cave, goes underneath Mingo Knob, and into my cave, into the Elk River. So it's actually taking rainfall from the Tigard Valley watershed and flowing underground into the Elk River. So that's at least, from Simmons Mingo Cave over to my cave is at least 5 miles, and then it goes another 7 miles underground. So what I'm saying is what's coming up at Cougar Mill is actually rainwater that's falling over at Mingo. And then also there's a cave up at Mace. There's a spring up at Mace that's been dye traced down to that pool there across from the Big Spring Exxon. That water that rises there in that big pool there along the road, actually some of it comes from a spring up at Mace up on top of the mountain. And that's probably 4 or 5 miles, but you wouldn't think that those two would be connected, but they are. Because that's just the local examples.
How do you go about checking that? Do you put dye in?
They use what's called fluorescein dye. It's a green dye, much like this, but it's more, it has chemical properties. It's completely harmless, but it has photogenic properties. It's the same dye that's put in your antifreeze that gives it kind of that shimmer yellow color. And so coal or an underground stream, it'll show where wherever it surfaces as this green and yellow color. So that's why they use the fluorescein dye, because it's very visible. The other thing you can do is put carbon traps. They put little cotton socks filled with activated carbon, and they'll put those in where they think the dye will come out, so that way they don't have to sit there and watch it. They come back, collect the carbon traps later, do some washing with ethanol, and then look for the dye in that ethanol, and that's how they confirm the dye tracing in that way too. I just saw a question along the wall. Go ahead, you have another one, Amy?
I was gonna comment that the sink across from Eamon's house was dye traced to these sprays.
Yep. Yep, that's probably it then. Yep. Any other questions?
Do you know of any systems that doesn't leak?
As far as,
Pipe leakage, malfunction?
well, with sinkhole collapse, there's no guarantee. You could look at thick-walled pipes and thermally welded pipe joints to where you don't have these gasketed joints, but you're still going to have penetrations into manholes are going to be weak points. And then, of course, anywhere if there's a collapse, there's no guarantee. It's just wherever the pipe strength will hold.
I heard, George, that you cannot run water and sewer in the same ditch because of contaminations from the sewer. Is that true?
That's I don't know. I think that's right.
I've heard that.
Or the water has to be above the sewer line by so many feet.
I do have copies of my remarks, minus the green dye, up there for anybody afterwards. There are probably 19 or so copies.
Any other questions? Okay, well, I thank everyone for their time. I very much appreciate the opportunity to speak and the questions. Thank you very much.